I wanted just to continue this morning's kind of tutorial classes, if you like, to try and give a kind of general introduction to the formation of complex molecules in space. I'll skip over quite a lot of stuff quite fast, I think, for those of you who aren't devotees of this subject, but several talks later through the week and in some of the parallel sessions will pick up some of the points I'm raising in more detail. So we live in a universe where there's a cycle of birth, life, and death among stars, and in that life cycle, chemistry thrives and makes molecules. What I've done is to list, there's 190 interstellar molecules detected to date. Some are tentative detections with question marks, but in these 190, which I've listed here, either in the interstellar medium or some uniquely in circumstellar shells around old stars. I've color-coded a number of these. So in red, I have the cyanopolyenes from HC3N right up to HC11N. So there's a carbon chain here. In green, I've marked the anions that have been detected now. Over the last decade, half a dozen anions have been detected in space. So from C4H minus all the way to C8H minus. I have in black, in bold black here, I've got hydrocarbons which are just terminated by a hydrogen. So they go from C2H, CCH, C3H, C4H, C5H, again all the way up to C8H. A lot of the chemistry that you see in this table, there's I think over close to 50 molecules here color-coded, are really carbon chain molecules. Despite the overwhelming abundance of hydrogen, as Florence mentioned to you earlier, in the universe, we see in interstellar molecules a chemistry where hydrogen, at least in some regions, doesn't play a very important role. The chemistry is really driven by carbon chemistry, by carbon-carbon bonds forming, but not so much by hydrogens adding on to these. So chemistry can be complex, but it can be complex in the sense of building very long carbon chains. And of course, more recently, there have been detections of the fullerenes C60 and C70, and just in the last couple of years, bands associated with C60 plus have been identified. So we go to quite big things in the interstellar medium. I'm not going to say anything about the polycyclic aromatic hydrocarbon component, which you can think of either as small dust grains or very large molecules. We certainly know that we see them all over our own galaxy and in other galaxies throughout the universe. We see them in emission, so they need an excitation source, which is generally nearby ultraviolet radiation. So we see them where there's sources of ultraviolet photons. And when you look at the emission properties, so this is a band of the PAH emission in the infrared, the typical size of these molecules are in the order of 50 to 100 carbon atoms. And on the order of perhaps 10 to 20% of all the cosmic carbon is tied up in these PAHs. But as yet, no individual PAH has been identified in space. Florence also mentioned that deuterium is very important in tracing both chemical processes in space and also tracing kinetic processes in terms of how molecules are formed and destroyed. There are around 30 or just over 30 molecules with deuterium in them, and some are very heavily deuterated. So Florence mentioned fully deuterated ammonia. There's triply deuterated methanol also seen in these regions. Lots of doubly deuterated species. And just recently with ALMA, Belfast has reported tentative detections of some of these very large molecules also containing deuterium. So deuterated methyl formate, for example, with the deuterations on the formate end, but not on the, also old detections on the methyl group. These sort of detections and the abundance measurements relative to their parent hydrogenated species can tell us quite a lot about chemistry that's going on. So again, this is another picture similar to the one Florence showed you of ND3, the detection of ND3, which shows that the fully deuterated to the fully hydrogenated form is around 10 to the minus 3 relative to d over h cubed, the cosmic ratio of a few times 10 to the minus 15. So there's an enormous enhancement of 11 or 12 orders of magnitude in deuterium seen in fully deuterated ammonia. That is driven by chemistry occurring at very low temperatures, driven by zero-point energy effects. So we know when we see very high fractions of deuteration in molecules that this is a signal for low temperature chemistry. That chemistry can be in the gas phase, but it can also be in the ice phase. And part of our issues around understanding astrochemistry is to try and separate out gas phase processes from grain surface processes. Flores also showed you these pictures of a dark cloud B68, seen in different lines in the dust, and also CO and N2H+. In these dark clouds, this is where these carbon chain molecules dominate. So in these clouds where the temperatures are around 10 degrees Kelvin, densities on the order, hydrogen on the order of 10 to the 4 to 10 to the 6. We have no ultraviolet photons. Chemistry is driven by cosmic ray ionization of hydrogen, molecular hydrogen, and helium. And this very rich chemistry, which in terms of dominating in forming carbon chains, occurs. So although there's a lot of hydrogen, a lot of H2 present, H2 reactions with carbon chain molecules, carbon chain ions, for example, are generally endothermic and don't go at these very low temperatures. Flores also mentioned that an important molecular content are ices in the interstellar medium. Again, this is just a different ice band spectrum of a deeply embedded source in the W33A molecular cloud, which shows these very deep vibrational bands from a whole range of molecules. One of the problems, or tentatively one of the problems with detecting molecules in ices, are that the fractional abundance that you can detect of a molecule in an ice currently is about 1% of the water abundance, or about 10 to the minus 6 of the hydrogen abundance in these objects. So our observations to materials in ices aren't great. If you use radio telescopes to detect molecules, you can generally detect species if the dipole moment is significant, down to about fractional abundances of 10 to the minus 12 relative to molecular hydrogen. So radio astronomy is much more sensitive to the presence of molecules than infrared astronomy, certainly in terms of the ices. But we know that ices have some properties. We know what their main components are. We know that we have information from comparing lab and astronomical spectra that the ices are layered. They're not uniform composition as you go down in depth through them. And we know that just from measuring the ice band features and working out how much material are in these ices, that, for example, in cold clouds, the amount of water and CO that are frozen on the dust grains are comparable to or even greater than the amount of water and CO in the gas phase in these clouds. So there's a lot of molecular material in ices in cold clouds. We don't know its full composition from observations, but we as I'll come to, we expect that the evaporation of these ices, or the desorption of these ices, play quite an important role in determining chemical complexity in regions of star formation. So hydrogen, chemistry is driven by cosmic ray ionization in these cold clouds, near very low temperatures. Cosmic rays strip an electron off hydrogen. The end result is the formation of H3+, which is a very low proton affinity and transfers its proton very efficiently to other species. Helium is also 10% of the total abundance of the universe is helium, is ionized to helium+. Helium+ is the opposite effect. It has 24 electron volts of energy when it collides with molecules, and it breaks bonds and forms fragments and other ions. But that destruction of molecules is also very key to actually giving you a reactive mix of species which enable complex chemistry to occur. Two-body reactions dominate in the interstellar medium. There's a whole sets of different types of reactions which have in some cases been well studied in the laboratory, in other cases not so well studied, that go together to make up the mix of reactions that determine molecular abundances. Three-body reactions, as Flores said, are generally unimportant, but can be important in the center of protoplanetary disks where densities can get up to 10 to the 13 or 10 to the 14 per cubic centimeter. The chemistry in general in building carbon chains is dominated by reactions of atomic and ionized carbon with, so these could be methyl groups of ions or radicals or ethyl groups and so on. So you can build by inserting one carbon at a time. You can build chains. Or you can react, for example, the ethinyl radical with both acetylene and acetylene ions to build up 2 carbon atoms at a time. There are reactions between neutral species that are very effective even at 10 degrees Kelvin. So the reaction between CN and acetylene forms the simplest cyanopolyene HC3N very rapidly at very low temperatures. And there are equivalent reactions that build up these bigger molecules. You can build from C4 to C6 to C8 and so on. And a lot of these binary reactions have been well studied now in the laboratory, right down to low temperatures for the neutral reactions, sometimes down to 20 to 30 degrees Kelvin. For the ion molecule reactions, quite often at 10 degrees and sometimes actually below that. So we have a lot of information on rate coefficients. We generate carbon chains very effectively. In general, molecular hydrogen doesn't react with hydrocarbon ions. Certainly once you get over three or four carbons and 1 or 2 hydrogens in the ion. So it's very hard to add hydrogen to these ions at 10 degrees Kelvin, and so carbon chains predominate the complexity of the chemistry in these cold clouds. What we find is, in terms of telling us ages of molecular clouds, for example, that if you go to typical densities of 10 to the 4 or so, it takes about a few million years for chemistry to reach steady state, which is where these abundance lines go flat when formation equals destruction. And at that point, you lock a lot of carbon up into carbon monoxide, the most stable molecule containing carbon, and the abundances of more complex things, these carbon chains fall quite dramatically. You can change things, at least in terms of abundances in time. So this is the curve for HC7N at the bottom here. You can change things if you allow material to freeze out, as it's likely to do in these cold clouds. So in this particular model, things freeze out by the age of 1 million years. And they can cause quite large peaks in abundances. As some of the material that normally destroys molecules and radicals and their precursors gets frozen onto dust grains. You don't get a steady state in this case unless you return material from the dust. And we know from our measurements, from doing carbon-13 measurements, for example, in HC3N, or doing the measurements of deuterium in molecules, that these strongly suggest that our chemistry in these clouds is dominated by gas phase chemistry, and indeed many of the other simpler species as well. I want to move now to talk about a subject that Flores also touched upon, which is the formation of, as he said, what astronomers call complex organic molecules, and I'll mention hot molecular cores as he did, and also something about protoplanetary disks. And part of the issues people are thinking about at the minute are, how does one explain the observed differences in abundance between the 3 isomers of methyl formate, acetic acid, and glycolaldehyde? How does one explain the differences in spatial distributions that now we're seeing with interferometers? These regions of high mass star formation, where hot molecular cores are seen, are very rich in molecules. So this is a part of a spectral line survey of the molecular cloud at the center of our galaxy, Sagittarius B2, which is about 1 million solar masses. Perhaps other than the black hole at the center of our galaxy, is the largest object in the Milky Way. It's very rich in certain spots in terms of its molecular emission. This is half a gigahertz of spectrum at 147 gigahertz taken with ARAM. There's lots of, I guess all you need to do here is just see the complexity of the lines, and although you can't see the formula, they're all long formula. So there's lots of complex molecules seen here, particularly ones now with hydrogen in them as opposed to the carbon chains. Carbon chains are harder to detect in these hot gas regions. And they've identified in 2 of these particular clumps in Sagittarius B2 that they've surveyed, in the N clump and the M clump, on the order of 102 lines per gigahertz in these regions. Lots of molecules, in the two objects over 50 in each, or around 50 in each of these, plus on the order of 50 isotopologues also seen, carbon-13, nitrogen-15, and so on. But lots of lines remain unidentified in these regions. So in Sag B2N, about 30% of the lines they've found are unidentified. About half of all the lines in N are unidentified. About half of all the lines in Sag B2M are unidentified. Many of these may be due to torsional, vibrational transitions from molecules that are already known, or different isotopologues where we don't have lab spectra to compare to the spectra. But there's a lot of complexity, a lot of molecular emission. There's almost no continuum you see across this source. All the emissions coming out in molecular lines. If you look at these regions, so this in this galactic center, there's lots of massive stars being forming that heat the gas to a few hundred degrees. It's very similar to other regions of massive star formation. You find that the chemistry is complex but different from cold clouds. And so what I've done here is to mark in green the type of molecules that now you see in these hot molecular cores. So they're not the carbon chains anymore. They're things like ethyl cyanide, ethanol, dimethyl ether, acetone, propyl cyanide, and so on. Methyl ethyl ether is on here as well. In general, one of the things we see is where we can compare, let's say, simple molecules with observations in cold clouds. So when we look at ammonia, NH3, or we look at methanol, or hydrogen sulfide, H2S, and so on, we find that in these hot regions, these hot molecular cores, that their abundances are factors of between 1,000 and 10,000 more abundant than the same molecules in cold clouds. So methanol abundance in hot cores is a fractional abundance of around 10 to the minus 6. In cold 10K clouds, its fractional abundance is around 10 to the minus 9. You find the same thing for hydrogen sulfide. In fact, it's a bigger enhancement of around 10 to the 5 in that case. Ammonia has got an enhancement of a factor of 1,000 or so in its abundance, going between cold material and hot material. The other thing to say is that many of these, as I showed in the earlier table on deuterated molecules, many of these species also have deuterium in them, which tells us that although we're seeing these molecules hot, perhaps 200 or 300 Kelvin in some cases, in some sources, that the chemistry that causes the fractionation process in forming these molecules is a cold chemistry. The chemistry is probably not as cold as it is in the dark clouds, 10 degrees Kelvin, but the D over H ratios turn out to be consistent with temperatures in the order of formation of in the order of 40 to 60 degrees Kelvin or so. So the molecules are much more hydrogenated, and where we can compare them much more abundant, but they're also deuterated. And the result is that the kind of consensus, as Flores was saying, is that these molecules arise from the result of chemistry either in ices or from gas phase chemistry following the evaporation of ices from dust grains. These objects often have very massive stars heating them internally in this case. So we have very small, very hot, very dense clumps of gas where we see these complex molecules. Many of them that we see in these sources are also seen in cometary coma, and I think Captain Watson is going to come back and talk about this later on in the week. We have lots of lines, as I've saw. Many of them are we call weeds. Can find useful information out of them. It can be difficult. So there's strong indications, as I said, that they're made on ices, and the chemistry that we're seeing is either material coming straight from an ice, or there's some sort of gas phase chemistry going on in these ices. We haven't yet seen these complex ones. I think, as Andy Trey said, the most complex molecule we've seen to date in discs is methyl cyanide, CH3CN. I'll come back to that point later in my talk. They're reasonably abundant, but it could be that our lines are just weak. Protoplanetes are very small objects. They don't have very much mass. It may just be a question of sensitivity. And maybe we haven't looked at the right parts of the spectrum yet for them. So models of the kind of chemistry that occurs in these hot cores are the equivalent regions around lower mass star forming regions, the so-called carinas, which are slightly less dense, less hot, and less column density, less material in them compared to the hot molecular cores. We can work out from the dust emission, from the spectral energy distribution, real dependencies of dust temperature and density, and that tells us that if you're at high densities, the gas and the dust temperatures are coupled. So that can give us a model for what the cloud looks like in terms of its underlying physical conditions. And you generally build chemical models from three sources. One is you try and ensure that you have the pre-chemistry right, the chemistry before the material freezes onto dust grains. So there's a low temperature, a cold, perhaps a dynamically evolving gas into a high temperature region. Follow ice mantle growth and also surface chemistry that's going on in this cold phase. There's a phase, again, that Flores mentioned, which is the warm-up and sublimation phase. It's possible that in this warm-up phase that you can, certainly if you have energetic particles and photons interacting with the ice in the warm-up, that you form radicals, and they begin to move when you get the temperatures of 30 or 40 degrees Kelvin in the warming ice, that they can build complex molecules. And in the end, you dump the ices back into the gas phase. And because you're at high density, you're at high temperatures, again, you can still have chemical reactions going on at these high densities. So you may have parents being evaporated off grains and then daughter products formed as that. The chemistry that goes on in these regions is both space-dependent and time-dependent because it depends on a material being warmed by a central protostar, which itself is evolving in time as it contracts and as it heats up. So the chemistry of these regions is quite complex. The molecular distributions will be very space-dependent, but also very time-dependent. And they can be important in terms of probing the gas and probing the history of the gas that we see. There are lots of processes that go on in ices. I won't go into the details here. A lot of our uncertainties in terms of modeling are around the importance of these processes in icing, or ices are trying to give some sort of time scales or equivalent rates to the processes that occur in ices. I just wanted to say a couple of things about these models. So this is an old model that Declan and Millar and I did, which was looking at a hot molecular core in a source called G34.3. We looked at instantaneous evaporation of methanol and ethanol into ices and followed the chemistry that occurs in the warm gas and makes daughter products, including dimethyl ether and methyl formate. And these daughter products form in about timescales of about 1,000 to 10,000 years. Eventually, over long times, the gas adjusts to being more the chemistry driven by kinetics in a warm gas at 300 Kelvin or so, and these abundances go down. So you can hope to, if you know enough about the source, to use relative abundance measurements of some of these molecules to tell you something about how long it is since ice has evaporated. And perhaps a little bit about what are the more minor components in these ices rather than the more major components. So Garrett has, a couple of years ago, produced a paper where he was interested in studying the formation of glycine and the importance of ices in glycine. And so he developed a rather similar model, much more detailed in terms of his ice chemistry, where he looked at both surface reactions and bulk reactions on the ices. So he kept a count of each of his mantle layers as the ice is formed and allowed reactions to occur in different layers. So this is a plot of fractional abundances relative to hydrogen against ages, where he looked at mantles which warm up either in a rapid time scale, a few times 10 to the 4 years, or a slower time scale. Dotted lines are ice abundances, so this is the methanol abundance in the ice. And when the methanol gets to 100 degrees or so, it can evaporate off the ice and comes into the gas phase. Formaldehyde comes off the ice because its binding is not as strong, comes off around 50 degrees Kelvin, and then undergoes chemical reactions and its abundance falls. But what you get is in these kind of models is you get a segregation in the terms of the kind of chemistry that goes on. So there's no methanol in the gas when the formaldehyde evaporates. So the chemistry you get from formaldehyde coming into the gas is different from the chemistry you get when methanol evaporates into the gas. And so the right-hand side, there's also a kind of time dependence. Things can come and go. So this is formaldehyde coming up again at around 50 K, but going away very rapidly. Methanol coming up at around 10 to the 6 years now and decaying. Now the timescales here are 1 million years and a few million years and a few 10,000 years in this. So the timescales are different in these two plots. But you get this kind of stratified chemistry that you can hope to begin to probe if you have high resolution instruments to do it, such as ALMA. So Garrett also made a model for glycine formation, again looking at whether the material warmed up quickly or slowly. It depends on a complex surface chemistry in this case. But again, so he was making molecules on the ice, letting radicals move and warm up in the ice and recombine. He had photons and cosmic rays interacting with the ice to generate radicals. But in the end, he makes predictions about how much so the black line here is the glycine abundance, how much glycine you might get out depending on the age of the cloud. And he's depending on whether you're in a fast warm-up or a slow warm-up phase, can make more or less glycine at the peak. Again, things drop off on long time scales at high temperatures. So temperature here gets up to 400 degrees Kelvin by the star warming material up. So this is the kind of state of the art. I should say that in terms of gas phase versus grains, there are pros and cons with each of these. We know certainly from some cases that a lot of gas phase chemistry depends on the recombination of protonated neutrals to produce them. We know that in some cases the protonated neutral doesn't recombine very efficiently to its parent, so protonated methanol and ethanol only give us about 7% or less than 7% of the time recombine to methanol and ethanol. In other cases, complex molecules do recombine a large fraction of the time to the neutral we're trying to make. But it's difficult to make complex molecules with lots of hydrogen on them in the gas phase. On grains, well, it certainly helps if you can make radicals in warm ices and let these radicals move and be mobile. So we certainly know that we see many of these complex molecules in very high abundance in these hot regions. We certainly see them to be highly fractionated in deuterium. So we know there's a chemistry that's going on that is predominantly a colder chemistry rather than the hot gas that we see. And we know from experiments on carbon monoxide at 10 degrees Kelvin both that methanol and deuterated methanol can be formed very efficiently. But we also detect some of these complex molecules in cold sources at maybe 20 degrees instead of 100 or 200 degrees. And there we need to think carefully about how do we get these molecules off the grains and back into the gas phase. There's some possibilities for that, but I think this is still open question. I want just to finish by saying something about disks, which are, you already heard, are complex objects, but they have, again, possibility of having rich ice chemistry because of their cold midplane. They have certainly, when the grains come in, the ices evaporate and form a warm molecular layer, as Andrew Trey was talking about earlier on. We have photons and X-rays from the central object that can interact with the gas and the grains in this region, and again drive the opportunity of driving quite a complex chemistry. And densities are large. And of course, as you go in toward the star, densities get up to a few 10 to the 12 or 10 to the 13 in the midplane. But temperatures go up to a few hundred, several hundred degrees, indeed up to perhaps 1,000 degrees as you get in toward the star. I'll skip over this because Anne mentioned this already, but we are limited in what we can see at the present time in terms of complexity. You can make models of these disks, chemical models of these disks, which you can determine the densities, temperature of the gas and the dust, and the radiation fluxes of ultraviolet and X-rays and so on at each point in a disk model, and do chemistry, which might include surface chemistry as well as gas phase chemistry, and a variety of mechanisms which return material from the ice to the gas as you move in toward the central star. So these predict. So this is just on the bottom here is a disk which is a radius of 300 AU or so. So this is just the abundances with vertical distance that is sliced at 300 AU. So from the midplane to the top of the disk, under a whole range of different desorption mechanisms for removing ice to dust. And I guess the only point I want to make here is that distributions for different molecules look different. But they lead to different column densities, different emission properties, depending on where these molecules will peak in their distributions, which one can hope to observe. The distributions are distributions you can calculate in terms of their gas phase species and also in terms of their ices. And indeed, most of the radial extent of the disk, most of the material is in ice by several orders of magnitude toward the gas, except when you get close to the central star. And it doesn't show up very well in these pictures, but there's large spikes in gas phase abundances as the ices get evaporated. And these ices have their own snow lines, where the regions from the central star at which the material evaporates because of individual binding energies on ices. Catherine will probably come back to this because I noticed from her abstract she's going to talk about comets as well as disks. You can begin to try and compare the model calculations to what you see in comets for these complex molecules. And I guess just the general point here is that what we're finding in terms of the models at least is that most of the large molecules that we're seeing in terms of our abundances between what's made in the cold cloud before you make the disk, the pre-existing material, and what you find in the disk itself, most of the comets are made in the disk rather than in the ice. I think I'll skip the next slide and just say something for a summary, since Wolf is going to eat me like the grandmother in the story. Carbon chain formation is really well understood. With lots of lab data, we can build complex molecules along carbon chains in cold clouds. We can test it out in the fact we see these carbon chains in the envelopes of carbon-rich AGB stars, and again, our models do very well about that. In terms of hot cores and carinos, we're likely to be driven by chemical reactions in the ice. We still don't know whether these are surface-dominated or perhaps bulk-dominated, and they're mediated by desorption mechanisms and some gas phase chemistry. So in these regions, the abundances are determined by a mixture of ice chemistry and gas phase reaction. I think the observations of D-bearing comets will help us discriminate these. To date, they point in favor of ice chemistry, but that may not be for everything. We're really limited by our uncertainties in ice chemistry, and there's a whole range of uncertainties: binding energies, diffusion energies, the actual composition of the ice, its porosity, how the particles and how cosmic ray particles and UV photons interact with ices. And a final thing, complex species are going to be difficult to detect from the calculations that we have done in this due to their low abundances and their very large partition functions, which mean that very little energy is spread over any one transition. There's lots of open questions. I just finished with those and leave you to read those, and thank you for your attention. Thanks very much.